Good morning. I'm Scott Anderson with BGC Engineering, and I'm here today to talk about case history in the future. And what's notable about this case history in the future is that at several points during and after the development of this project, the team was all able to look at one another and say, hey, we all saw it the same way. And they did that through something called augmented reality. And this HoloLens that I'm wearing here has been showing a hologram. This hologram's been here the entire time you've been in the room this morning. And it shows the location of this important case history. It's a really special place. This valley here has had, you are seeing it, right? Yeah, I think you are. I've asked them to turn the monitors off so you don't see the monitors, so I can't ever see what you're seeing, but I'm going to trust you follow me. The valley here has had important cultural artifacts for over 1,000 years. The ridge line up here has trees that are equally old. There's a very special coastline over here that's getting more and more rare. The only problem is that what's changed through the years is the need to move people and goods along this red line, which is the existing highway. It used to be perhaps a couple horses a day, and now it's several thousand cars a day. And the sea level here is perhaps rising, and there's some coastal retreat and erosion that's threatening the highway. In fact, there have been some slip outs and even some fatalities. So things need to change. And the owner of this project has been showing the public for a long time how there are some options that we could retreat from the coast and get a safer and better performing facility. And they look like these lines on a map. Using LiDAR that's available from the publicly available LiDAR from the LiDAR clearinghouse, the owner was able to look at some things here, and I won't step off the stage. But they can see the hummocky ground here. They can tell there's a major earth flow that's going on as well. It's not just coastal retreat in this problem. They can also look over here and see where the alignment goes across the headscarp of a major deep-seated landslide that goes down perhaps below sea level. And they recognize that this is a really challenging geologic environment. So they commission some geologists to go out and map. And the geologists bring their rock hammers and their Brunton compasses, and they've got their GPS, and they head off into this dense forest. Unfortunately, they can't find anything to hit with their hammers. They can't find anything to measure with their Bruntons. Their GPS is hardly receiving a signal, but they're wearing HoloLenses because the HoloLens is completely self-contained. I'm not attached to anything. And they bring their HoloLenses into the forest, and they can zoom in, and they can make measurements, and they can see how the little terrain changes that they're observing in the field, in the forest, are related to other things. And they're able to identify these polygons, and these polygons map as landslides. And they recognize that the lines that have moved to the right here have moved away from the coast indeed, but they have not moved away from the problems of landsliding. And they recognize this is a really important thing, and so they go to the public and the politicians that have been dreaming about these other retreat options for a long time and say, this problem just got more complicated, it's not so easy. And they're able to do that by bringing HoloLenses to a public meeting and having people wear them. But there are only so many HoloLenses, and hundreds of people showed up at this meeting. And so the people that couldn't wear HoloLenses used the viewfinders on their smartphones to see this hologram, just as those wearing the HoloLenses were able to. And when that meeting was over, they were all able to say, hey, we saw it the same way. This is challenging. It turns out there's 4 key areas that we're going to visit today where the success of this project hinges. We're going to start here with the one in the front. And even if you weren't a roadway designer and didn't work with landslides, when you put the design template of what would be necessary for a steep grade and a radius of curvature for highway speeds and so on, you'd recognize that, remember these brown things are landslides, you'd recognize that you have to put a 100-meter high embankment on an existing landslide to make this green route work. You'd have to cut through its lateral margins, and this would be challenging and may not work well in the future. Because of that, they said, well, maybe the devil we know is better than the one we don't. Let's see what we can do to get across the headscarp of this major deep-seated landslide. They had 2 routes here. Perhaps they restore the existing one, or they build another one. But since they've been studying this area for a long time, they have change detection that's been developed, and they know the site very well. It's interesting how this change detection was determined because there actually were multiple stages of LiDAR that had been collected, and they could subtract these images and find out what had been going on and really understand the geologic model. But not only was LiDAR used, satellite-based INSAR was also used to determine how this slope was moving. And you see the proposed upper alignment and the lower alignments here where they'd be. But interesting, all the drones had all moved down to LA and because there's an impending earthquake where they're going to be needed in the hundreds and thousands. And so they didn't really have drones here, but it didn't bother this owner because they had learned about something called microsatellites and nanosatellites, things the size of a can of beer or a loaf of bread, and they launched their own. They throw them up in the backyard, and they've been monitoring this site with their own microsatellites for a long time. Drone pilots are doing something else. So they know this very well, and the issue becomes there's only really one way to manage this, and that is with deep ground anchors. And so they know the kind of design. It's going to take the force of the largest anchors we ever use, and large numbers of them, rows of them, and it's going to look something like this when built. But the question really here is about constructability. So the owner engages the contractors and says, look, can we do this better from below or from above? Is there some preferred alternative from a constructability point of view? You can see the nice extruded concrete rail here that's been printed on the project in the future. So at the end of this meeting, they're all able to say, hey, we saw it the same way. We understand constructability and how this is going to be built. Now, the problem really starts back at erosion along the coast. And now you can see down here on the coast, one use for drones still in this environment here is when the ground gets very steep, satellite and aerial-based things, you need the lateral look. So this is a oblique aerial photography that's used to structure from motion, a process to create this point cloud. So this is not just a photograph, but it's a 3D model. You can see the coastal erosion. You can see a scar here, but we're going to go visit this little area in the box. And we can come right in here, having never been on this coast and not being able to get to it because it's not very accessible. We can see the modes of failure. We can see the cracks that are opening up here and can start to envision what we might do to stabilize this coast so that it stops eroding so fast. And being a point cloud, we can actually solve for what the planes are that define this, and we can look at along the edge of the plane and see how smooth it is and see why perhaps this thing is rotating out in order to slide, and we can do the analysis necessary to figure out what it takes to stabilize. We may decide, in fact, that it's worth looking at this from below, and we say, oh, look at that up there now. That gives me some perspective on those orange slides, the planes I couldn't see before, and we may decide it's useful to look way down into the ground and look at it as if we were high up. And we've got, of course, that capability. I'm going to put this back in the middle. And there's one other place we want to visit on this trip, and that's a bridge. And there's a bridge that's located to the north of the project. And the geologist that did the mapping thought perhaps this was on a landslide, and we're going to have to decide whether or not it is. The bridge looks like it's been extruded like Play-Doh through one of those little nozzles or something, because we still design bridges in 2D in the future, although we talk about going to 3D. It's all done on plan and profile sheets, so we really don't know what it looks like here. But geotechnical data are three-dimensional data, and so we do a conventional exploration of this bridge site, which just has a couple borings on this abutment, and SPTs that are taken at 5-foot intervals. These disks show the value of the end value. And this only one hole was accessed over here on this abutment. And the young engineer that was out doing the drilling every night came home. It takes a day to drill one of these holes in this environment. Every night came back to the hotel and put on the HoloLens and looked at the results that came in from the field, dialed up the senior engineer back in the office, and they talked about what they were seeing and what it meant. They both recognized we have no idea, any better idea if this is on a landslide or not, so we need additional information. So to get additional information, they mobilized the cone penetrometer out to the site, and they looked at things like friction ratios and tip resistances and cones. They got more of these soundings in. They still didn't really understand things, and so the senior engineer back in the office said, we need more information still. And he says, the problem is I work with this project manager, and this project manager is really tight. Doesn't like to spend money early in the project because the project manager always finds that money is needed later on when problems happen. And the senior engineer got this idea, said, you know what? This is the tool I need to help my project manager know that if we invested a little bit of money up front, we'd save a lot of money in the future. And so brought the project manager in and was able to convince the project manager that we need additional information, perhaps some geophysics to look for discrete slip surfaces and that kind of thing. And so they were able to do that, and they were able to recognize that really they're going to need some inclinometers installed in this site in the future to understand if it really was on an active slide or not. So we visited these 4 areas, and you know, right now we're back to just lines on an image. And there was a time, and so by doing this and sharing this thing, I want to point out that we looked at using augmented reality to look at this case in the planning stages when we're looking at which route to go through. We used it for geologic mapping in the forest here. We used it for subsurface investigation at the bridge site off in the distance. We used it for analysis along the coast, and we used it for constructability in this area here. There are many ways that we used augmented reality to all see it the same way in this project. There was a time when we thought that just putting these bold lines on a big poster board in the back of a meeting hall was a good way of communicating. But when you think about it, bold lines on a planar sheet of paper is really not much different than trying to speak louder to someone who speaks only a foreign language. If a person doesn't understand the 3-dimensional environment and how this green line might lie on there, putting it on a nice poster board in the back of the room doesn't really help. And similarly, we talk a lot about, in the present now, we talk a lot about where should the boring logs be? Should they be in an appendix? Should they be on summary sheets? Should they be in the geotechnical report so everybody has to read that? And what we're really doing, though, is we're basically assuring that everybody sees it their own way and not the same way. So in the future, we'll use augmented reality to reverse that. Now, I'm going to close this out right now. And I've got a little app over here, GIASCE. I'm going to take this off. I think I am. And talk to you without my headset on, which feels good. But the headset's not terrible either. What I want to say sort of in closing is that hopefully you saw something a little different today, and it felt different. And if it felt different, it's probably because you saw me and I saw you, and we both experienced this hologram that was right here and had been here all morning. So our reality was augmented, but it was a reality, and we have the same understanding of what happened. I also want to call attention to the fact that I'm the only person in the room today that saw anything in 3D. I was looking at a 3D image. You were looking at 2D images, the 2D projection on the screen. And you don't get that until you actually get into the 3rd dimension with some device like this. And that's a whole new level of understanding that I hope you get sometime. I want to just thank my clients that made all this possible. They had no idea I was going to fabricate a story with their work, but I did. The Federal Highway Administration, and a partner with Minnesota DOT, Caltrans, the British Columbia Ministry of Transportation, and CN Rail were all projects that I stitched together here. And I want to thank BGC's programmers. We have programmers that know as little about geotechnical engineering as I do about programming, but they make all this happen, and our partnership with Microsoft, which makes the hardware that allows us to do this. Thank you very much.